shortcut like this thing? And
Well,
like,
there's no such thing as a neutral pH indicator.
needed venting.
None of them
And
really
so
do
then
that.
she goes, or no.
Okay.
So it's gonna be slightly acidic. Huh?
Like
Just get a really light color.
Yeah, so I think we might want a slightly acidic one, because what the indicator will show is that all the carbonate's gone then.
Yeah.
So at that point, so we want to make sure that at that point, so
I always had
I think
special
we want a
instructions
slightly
too on those
acidic
stuff.
indicator.
Yeah.
See, it always stresses me
No,
out.
I'm thinking like how
So
acidic
I'm
of the
like,
indicators
say,
color
I
we
don't
need to
know.
use.
Oh, for different indicators, they have different pHs.
Like phenolphthalein is a basic one.
Medium dark.
Yeah. While there's ones that are like only show colors at 12 or only show colors
You
at
want to
2.
try it?
Gotcha.
Try it. It's really
Okay.
strong.
So
I
because carbonate's a base and we're neutralizing with HCl. If we start seeing color once the
But I mean, that's
HCl
what it
what
comes with. It's fine.
acid, that means all the carbonate's
Oh my
gone,
God.
and that's probably the one we want.
Yep.
Really strong.
So we don't have to do
Starbucks
a
double
note for
shot.
that. for
2
this.
pumps of
No.
coffee, 3 vanilla.
Good.
She just wanted us to look through the chart and determine what type of indicator we should use.
Yeah, it's
Okay.
good.
Are we
but
supposed to have that written down anywhere or just know it?
I just know what I think, but maybe write it down.
Well,
I hear that I'm in the presence of professional chemists because I see like some keywords, titration, I see, which would probably not. I wouldn't hear that it would be physics or engineering or biology. So, who you are and what are you doing? So it is a physical chemistry class, and we are so impatient to eventually get to prediction of outcomes of measurements of some instruments, like characterizing materials with their spectra and other, I don't know, heat capacity, color, reaction ability to burn. That's through activation of reaction bearings, but like, instead of doing this literally and directly, we are bothering ourselves with quantum theory. And the motivation to do it is that properties of atoms and molecules are defined by motion of electrons, who are so energetic, impassioned that they can't stay still, and we need to know how they move. You did nice presentations on fundamental postulates of quantum theory. Like, they are not practical recipes, but they give a framework how to think and how to plan description of properties of these electrons in molecules. Right? So you are certified experts in postulates and in some other things. What else do we have in the class? What is our knowledge baggage? Anything you remember or you think is relevant, of course. Like, what about the future? What can you do with that?
predicted.
Excellent. I see you're doing here in class. So you can predict future of an electron, and you know how to mathematically define past and future. You just write psi wave function at different time in the past and time in the future. This is good. Also, you probably are acquainted with concept of operators, and you even have an intimate acquaintance with one of the operators, with the operator of momentum. What else? Let's just scroll through our memories and try to, or through the notes. Which problem is typically solved in very basic, low level of quantum theory? Some of you was riding with me the elevator and mentioned the right keywords. So
Particle in a box.
this is one of the applications, but more general. Yes. So eigenvalues, eigenvectors, eigenfunctions. So So it is the most popular problem, and even people who are not big experts in quantum theory speak this language and solve this problem, at least in the course of studies. We cannot avoid it. So there are operators, there are some rules how to construct them, and then there are functions that are eigenstates of these operators. And those things are building blocks to predict the future, to describe electrons in the molecules or materials in general. This is a good list. Operators, momentum operator, eigenstates problems, 3 ways to predict the future. What else? Important thing. Most, well, not most, but the closest one to our goals and motivation. So all this boring theories. So if you know wave function, but our employer wants results of experiment, how do we connect wave function to the outcome of experiment?
A lot of math.
Huh? Well, well, lots of money just hiring the right person, solving all problems. But mechanistically, we already know the recipe. Maybe without too much details. And I'm not yet well enough acquainted with your names, but one of the presentations was on this connection. I remember we had a debate and arguing this one. So if there is a, we discussed it with everyone. If there are a lot of measurements and our preferred system of interest is not equivalent at each measurement, it can be in one state, another state, superposition, but we want to have a solid number to compare to whatever comes out of measurement. Just think about it. You do not need to answer. I will approach from different side. If a system is an eigenstate, then a measurement will give the eigenvalue of the operator. But if it is not in the eigenstate, it can be something different. And then one uses the concept of expectation value of an operator that corresponds to something that we need for the measurement. So you take operator, quantum operator, and multiply it by wave function from left and right, and then integrating and getting the outcome of experiment. Okay, so it is more or less what we are expected to get. Enough background, and it looks like we are done with the first chapter of basics. So we have bought a car, and we need to ride to a picnic. We just need to find some nice sightseeing to explore. So with these tools, from now on, we will be exploring different applications, different problems, with ramping up the level of complexity on one hand, of course, to torture young people, as you probably think about this course. And from other side, to approach to systems complicated enough to be comparable to real life. Because if you start something really practical right now, we will die. We do not have enough muscles, mathematical muscles to process it. Or we don't have enough skills, enough experience to predict difficulties and have the tricks how to bypass them. But if you start with something simple, we will suffer this abstraction from real world, but we will come to the level when we can do useful things. Make sense? Okay. So what are we going to focus on as the simplest possible problem? Brandon knows the answer. London knows the answer. I'm just looking who is smiling. Okay. So we are talking about electron. And molecule or atom is electron in the vicinity of something attractive, like nuclei. But suppose we have an electron that travels and is kept by an ion. Before, I don't know, electron departs one molecule, approaches another molecule, electron transfer. But in between, especially if the molecules are in vacuum, there is a time interval when it is like standalone electron, not bound to anyone. Bachelor electron. Or we can imagine a fake universe where there are no humans, no planets, no stars, no molecules. There is only one electron. But we want to mathematically rigorously describe what this electron is doing based on our luggage of knowledge, based on the theories that we've got. So it is a task for, I don't know, 5 or 4 meetings. So, before we go to details, I want to make a couple of administrative announcements. Otherwise, we all get too excited into science and forget about that. Remember the email with homework. I apologize, I was planning to print it, but I was not lazy to print it. I just forgot because I was excited and rushing here. But if you all lift hands if you didn't get the email. Okay, meaning that everyone got the homework and everyone is happy about trying to do it. So there is something in common between you and me. We all want you guys to have a maximum possible grades. For you, it's your career. For me, it's record of excellent teacher. I will brag to my colleagues, so see how efficient I am. They have all good grades, but I'm expecting a little cooperation from your side. So, no homework 1. Let's assume everyone got K. Then everything will go better. So, homework 2. I just show this what we do during this assignments, and then I will make an announcement what will be a program of tonight lab session. Again, no one can twist your arms and bring you to the lab tonight. It is like in the regulations there are only 3 hours, lecture hours. So it is your free will if you come there. So it's highly recommended, but not mandatory. Homework. Some of you may have enough mathematical background to be flexible with Fourier transform. But if you are not, it's not a big deal. It's one of the easiest concepts of the advanced math. So you can look in Google or some textbook. It will be sufficient. It's just same. So in application to our course, the Fourier transform is exactly the procedure of finding expansion coefficients. What we finished on our last meeting. So that in order to predict future, we need to process initial condition into the expansion coefficients. Right? So multiplying initial wave function times eigenstates. In some sense, in some cases, it is literally the definition of Fourier transform. And we want to practice it a little bit to help our lecture material go smooth. So you look what it is. Then there are two types of Fourier transform, or Fourier Laplace. So one can expand function in basis of oscillatory sines and cosines, Like here, any function can be represented as summation of cosines with different frequencies, and one needs to find expansion coefficients. And another form where any function can be represented as summation of exponentials, oscillator exponentials, but idea is the same. So the task is to consider function that is periodic but not harmonic, like a beast, a model of a beast that have half of teeth. One present, one absent, one present, one absent. I don't know, maybe you have some more profile of a castle wall. So periodic but not harmonic. So this function, which protrudes infinitely to the left and to the right, can be converted into the form of this Fourier transform. So you may want to find coefficients A and B. Do not feel scared. The homework assumes some investment of time. So do not be surprised if you look and you do not see Angels bringing you answer next time. You need to sit and analyze but it is not deadly thing. If you invest this amount of time, you'll get the right answer, and I will be happy to chat on this. So, second one, if you will listen and take notes of our today's meeting, you will completely address. You just copy paste from what you will do today. And the third one is another form of Fourier transform. So you take this function, multiply it, and integrate, and just report what you get. Here is X, right now it is blocked by this sound detector. It works. This green stuff pop-ups when you shoot or make some noise. Okay. You got general idea what is in cool. And let's bring it to the class maybe from now. So we have the whole weekend. Some level of being scared will be present in your souls. And it is a healthy. I anticipate it. Main reason of you being scared of mathematical tasks is to move you towards computational modeling, which is 100 times easier. So some problems that are hard to solve by pen and paper can be made in a few minutes just by writing 2 lines code or whatever, or using some software as a big calculator to solve quantum problems. So we will have another chapter, segment of our course with very basic, very primitive modeling using so-called MATLAB software. And it is fine if you never saw it and never used it. So most of our evenings on Wednesdays will be related of MATLAB for quantum theory or for physical chemistry. Again, you can decline to come. You will survive, but it will be harder. So if you come and just half sleepy listening, it will make your life easier. At least from my point of view. Any questions about administrative side of the course? Objections? Yes?
I guess I am just curious for like that recitation class or that one later tonight. When we start working with things like MATLAB, will we be meeting in some kind of like computer lab where we'll all be working on the same thing?
I think it's in the big lab downstairs.
I think it is 122.
Okay, perfect. I remember seeing QBB, but honestly, I just thought it was
Downstairs.
Okay.
I can be wrong with number. It can be 130. I think it is 123. But if you just walk in the corridor and hear laughter and loud talking, you recognize the faces.
Okay,
It's 130.
perfect.
132.
Huh?
132.
Okay, yeah.
Thanks.
So I was going to give you money, but I forgotten to print it, like fake money. Like here in this country, the currency unit is dollars. What is the currency unit in Europe?
Euro? Euros.
Euros. When did they introduce it?
Depends on which country you're talking about.
Germany.
Germany? That was earlier on.
2007?
Maybe. I don't care. I left it in 2000. So before this European Union and common currency for the whole Europe, they used to have national currency. And the currency in Germany was German marks, Deutsche marks. So whose faces are shown on American currency? Presidents. Guess whose faces are shown on this obsolete German currency? Well, different people, but I'm impressed by 10 marks note. So,
Gauss, isn't it?
yes. So he's a scientist, mathematician, not a president. So this, I should bring more of this money and distribute. This is a very useful and important handout for our class. You can, what are your class notes? My class notes are money. I do not bring anything else. And in these circumstances, it would be very. So if you focus your glance in this area, it shows a function that is introduced by the scientist. And we will be dealing with this function for 4 minutes. So we can bring money as a class didactic helping material for a week or even longer. So it's exponential to the power minus second power of argument, e to the power minus x squared with some garbage constants. Well, not garbage, but I'm lazy to memorize. It's just zoom in. So here is our plan, and we will not complete it today. It's just beginning, but we go through several steps. So no one was objecting, maybe because even if you do not like it, maybe just because you're so polite, but no one was objecting to study electron in vacuum. And you are growing hope of world science, meaning you develop your scientific type of thinking. And before we start doing boring math or exciting experiments, we may use our common sense or previous scientific experience and develop hypothetical statements, like what are we going to get? Like math is a servant of a chemist and physicist. It's not a standalone thing. It has no value. It's just a servant to us. So which order we want to give to ourselves or to a mathematician whom we hire? Like on one hand. On another, if all our plans will be completed, if we travel to a picnic in a desired direction, which sightseeing are we going to see? So which properties of electron in a vacuum we may anticipate and then prove right or wrong? So anything you think anything you were thinking starting from kindergarten about free electron in a vacuum? Just share your vision. Before we start rigorous treatment, anything is okay.
I don't know, this is probably the wrong path, but I guess I maybe object to going down that path just because there'd be no kind of movement or anything that we could like get from the electron. There's no forces if it's just the electron, so there should be no movement along with it.
Good. So, no. What did Newton told you?
There needs to be a force for some
Yes,
kind of
but
movement to actually
before he started talking about forces, what's his first law?
An object in motion tends to stay in motion.
Yes. So you're right in the aspect that if we prepare electron to stay still, then no one will make it to move because no one else is present in this universe. But if you launch it to move, it will continue to move. So we may rediscover this simple thing. And x of t, if we decide for its average position, would be position at time 0 plus velocity, which is momentum over mass, times delta t. Right? It is what you wanted to suggest.
Mm-hmm.
What else? What else do we expect? Let's recall our discussions about probability, interpretation of the function, about the nature that electrons, even with very small energy, it likes to move. And it likes to occupy more space than it is allowed. Aggressive expansion. So suppose we did all our scientific skills and apparatus to squeeze electron and place it into a very small amount of space, like a cube or maybe a sphere. But then we remove any constraints and let it sit. What would you expect? Will it shrink or expand or stay unchanged? Just intuitively.
I would think unchanged.
Unchanged. Any other opinions? With arguments or any without arguments? Well, based on the question, you can guess that there are some other opinions. So shrink or expand?
I guess expansion.
Why?
I guess because if you constrain it within a small area and then you open up that box to a lot larger area, then it has room to expand due to disability.
This is a very good scientific hypothesis. So we will set up our whatever 4 meetings exercise as to prove right or wrong 2 hypotheses. First, that it moves according to initial velocity, and second, that if you have distribution of probability of electron to reside at a specific space, the area taken by this distribution will expand. Maybe we will find otherwise, but it is at least something we can anticipate, and then we sharpen our efforts to focus on these 2 aspects. And then it will be less philosophical, more specific, more concrete. Expanding electron. Yes or no? How much does it expand? And here is what we already discussed. We know concepts of some plane wave, Schrödinger equation, eigenfunctions. ways to predict future by expansion of initial conditions, right?